Black holes are one of the most intriguing and mysterious phenomena in the universe. Today, I'll take you on a journey to explore the evidence that proves their existence, the models that help us understand them, and why they are among one of the more well-supported phenomena in modern astrophysics. Let's dive in. So what exactly is a black hole, and how do we go from theoretical speculation to solid evidence? A black hole is a region of space-time when gravity is so immense that nothing, not even light, can escape. They form when a massive star collapses under its own gravity after exhausting the nuclear fuel that keeps it stable. At the heart of a black hole lies a singularity, a point of infinite density surrounded by an event horizon, the boundary beyond which escape is impossible. Historically, the concept of black holes dates back to the late 18th century, when scientists like Jean Michel and Pierre-Simon Laplace proposed the idea of dark stars, objects so massive they could trap light. But these ideas remain purely theoretical due to a lack of observations. In the mid-20th century, J. Robert Oppenheimer and his team demonstrated how massive stars could collapse in singularities, reigniting interest in the concept. By the 1960s, John Wheeler coined the term black hole, and astronomers discovered quasars, bright objects powered by supermassive black holes at the center of galaxies. Thanks to these foundational steps, black holes have moved from theory to observation, and now we have remarkable evidence proving their existence. Let's take a closer look at the observations that provide direct evidence of black holes. Stellar orbits around Sagittarius A. Sagittarius A is a supermassive black hole at the center of the Milky Way, about 26,000 light-years from Earth, very far away. Over decades, astronomers have tracked stars orbiting Sagittarius A. One star, S2, completes an elliptical orbit every 16 years. During its closest approach in 2018, S2's light was redshifted, confirming the immense gravitational pull of Sagittarius A. These observations provide long-term, repeated evidence of a supermassive black hole. Gravitational waves detected by LIGO. In 2015, LIGO made the first detection of gravitational waves, ripples in space-time caused by two black holes merging 1.3 billion light-years away. The signal matched the waveform predicted by general relativity, confirming Einstein's theory and proving that black holes collide and merge. Since then, LIGO has detected dozens of similar events, providing a wealth of data about black hole properties like mass and spin. The first image of a black hole. In 2019, the Event Horizon Telescope captured the first image of a black hole at the center of galaxy M87, located 55 million light-years from Earth. The shadow and surrounding photon ring matched predictions from general relativity. This image offered direct visual proof of a black hole's existence and opened new doors for research. So, how do we interpret these observations? Let's explore the models that support our understanding of black holes. General relativity. Einstein's theory of general relativity describes gravity as the warping of space-time by mass and energy. It predicts phenomena like singularities, event horizons, and gravitational waves. Observations such as LIGO's wave detections and the shadow seen by the AST perfectly align with these predictions. Accretion disk model. Accretion disk models explain the behavior of matter spiraling into black holes. Friction and heating in the disk causes it to emit high-energy radiation, like the X-rays observed in systems such as Cygnus X-1. These models also account for the photon ring seen in the EHT image of M87. And orbital dynamics. Orbital dynamics models describe how stars and gas move under the influence of a black hole's gravity. These models explain the motion of stars like S2 around Sagittarius A, revealing the mass and location of supermassive black holes. So, with these observation models, let's assess just how convincing the evidence for black holes really is. The evidence for black holes is both compelling and comprehensive. Each observation aligns with the theoretical models, strictly the case for their existence. The waveform detected by LIGO in 2015 revealed key properties of black hole mergers, such as their masses and spins, all consistent with general relativity. Multiple detections by LIGO reinforce this evidence. The orbits of stars like S2 around Sagittarius A provided repeated, long-term proof of a supermassive black hole at the center of our galaxy. These observations not only confirm Sagittarius A's mass, but also test general relativity in extreme gravitational conditions. The 2019 image of M87 offered direct visual proof of a black hole's shadow and photon ring. The image's size and shape match general relativity predictions, and the bright photon ring aligned with accretion disk simulations. These observations, backed by robust models, leave no doubt that black holes exist. They're one of the more well-supported phenomena in astrophysics. So, do you think black holes exist? Don't let the thought consume you. Thank you.